based on calculating the rebar stress. So our initial design is, this is initial design, T12 at 150, and we find that the rebar stress is 144 MPa, which has exceeded the 115. So we increase the reinforcement, right? And we change it to T12 at 110, and based on the rebar stress is 115. Okay, and then they just stop there. Okay, so they did not go through the calculation of crack width in this example. So, but I use this example to show how the crack width is to be calculated. Okay. All right. So here, the calculation of crack width. This formula, W max, maximum crack width, is equal to 3 times A crack epsilon m, 1 plus 2 bracket A crack minus C minimum, that means the minimum power, and H minus X. Here is A crack. Okay. So the X, basically the X is the neutral axis. We have calculated the neutral axis to be 46 millimeter. So this is the thickness, H, this is D, okay, and then this is X. Okay, H is 200 millimeter, D is 150 millimeter. Okay, so and we need the, what is H minus X? H minus X is, this is H. H minus X is this, which is the tensile zone, right? This is the tensile zone. Okay, and then D minus X, that means the effective tensile zone. Okay, so now we have the X. So let's calculate the H minus X. The tensile zone is 200 minus 46, which is 154, right? Is that correct? 154 millimeter. Okay, and then D minus X. D is 150 minus X 46 is 104, is that right? 104. Okay, right. So, because we need the H minus X or D minus X to calculate epsilon 2. Okay, right. Now, and the other things that we need is, okay, A crack. What is A crack? A crack is in the book. You see A crack. So we are using this formula. Okay. The A crack is the distance from the point at which the crack width is being calculated to a point of zero concrete strength. Okay, as illustrated in figure 11.6. So they use 11.6 to illustrate 11.6. Okay, so this is A crack. The position at which crack width is being assessed. Let's say you want to assess the crack width here. So A crack is from this crack to the surface, the nearest surface rebar. Okay, so yeah. So I want to evaluate A crack. I want to evaluate the crack between the two bars. Okay, all right, because that is where it is the most critical. Okay, all right. So A crack is this distance, right? And this distance, okay, to this, to the surface, okay, the surface. Okay. So how do we calculate A crack? So we calculate A crack based on this triangle. Okay. So from here to here is half of 150, right? Okay. And then from here to here, what's the value? See, here is, this is 75, okay? And from here to the center line of the bar, okay? To the center line of the bar, the cover is 40 millimeter, okay? And we are using T12 bars, right? T12 bars, right? So this distance will be 40 plus 6, right? So 40 plus 6 is 46. Okay. Fortunately, I can run out. See what this one has. Okay, so this is 46. 46. So what is it? What is this distance? Using the Pythagoras theorem, right? Square. This should be the square root of 75 square plus 46 square. That should give me 87.98. So let's say 88, right? Here, this is 88. Now, A prime is not 88 because 88 is from here to the center line of the rebar, right? So you want it to be the surface of the rebar. So it should be 88 minus the half of the diameter, which is the radius, right? Which is 6. This is equal to 88 minus 6, so it is 82. So A crank is 82. Okay? So A crank we already calculated. So we need the epsilon m, right? Epsilon m is equal to epsilon 1 plus epsilon 2. So how do we calculate epsilon m? This is the side view of the slab. View of the slab. So this is the rebar, okay? This is the X, okay? Now, based on the T12 of 150, our rebar stress is 144, okay? So the stress divided by the Young's modulus gives you the strain of the rebar, of the steel, right? So 144 MPa divided by 200, 10 to the 3 MPa. So what is that, right? 144 divided by 200, 0.72 or 7.2 times 10 to the negative 4, right? So this is equal to 7 times 2 multiplied by 10 to the negative 4. Okay? This is a strain. Strain basically has no units. Okay? It's basically millimeter per millimeter. Alright? Understand? This part understand? Okay? Means now our epsilon, the strain of the rebar, okay, is equal to 7.2 times 10 to the 4. Okay? Now, what is epsilon m? So we have this. We have okay. So this is epsilon s. So this is epsilon 1. Okay. Sorry, because just now I went there to get the ink, but the black one and the blue one, there's no more. And I fill in the red one. Somehow the red one not giving me any color. Now it's giving me so this is epsilon s. Sorry. epsilon s is here.
Dah bisa semua nggak sih? Dah ada yang bisa kan?
Epsilon s is epsilon 1, right? Epsilon 1 obviously is bigger than epsilon s, right? So epsilon 1 is equal to epsilon s multiplied by a factor multiplied by h minus x divided by d minus x. Okay? D minus x is here, h minus x is here. Okay? So what's that value? Someone just calculated. H minus x is 154. 154 divided by 104 is 1.48 multiplied by epsilon s is 7.2 is so 1.066 times 10 to the negative plus 10 to the negative 3. Right? Just verifying my number. Is that right? So we have epsilon 1, which is the strain at the concrete. This is the strain for the steel. This is the strain at the concrete. Okay? So epsilon 2 is calculated by this formula. For 0.1, this is for 0.2 millimeter crack width. Millimeter. 0.1 millimeter crack width will be, instead of 1.5, it will be 1.0. Okay, I think if you look at the book. Okay. All right. So epsilon 2 is 1.5 BT. What is BT here? The width, right? Remember we are designing this wall per meter width on a per meter width basis. So this BT is 1000. Okay, and h minus x is 154. A prime minus x for the slab, a prime minus x basically is the same as h minus x. Okay, because a prime is from the top to where the vertical distance from top to where you want to calculate crack width. So from here to here is my a prime. Okay. Alright, so A prime in this case is the same as H, alright, for the slab. For the beam, because the beam you can calculate the crack at the side, so the A prime could be different from the H. Okay? So we have basically A prime x is the same as H minus x, which is 154, D minus x is 104. Okay, so what do we have now? Is for 0.5. So what do we have? So 1.5, 1000 millimeter. Okay. H minus x is 154. And A prime minus x is also 154. And 3. Okay. ES. ES is 200 gigapascal, which will be 200 times 10 to the 3 megapascal, right? It's 200 times 10 to the 3 megapascal. Okay. This ES expressed in terms of MPa. Okay. And AS, what is an AS? AS is T12 is 150. So T12 is 113, right? Okay. T12 is 113. You can either you can either do it based on 1 meter, okay? All right. And then here the AS is how many bars? 1000 divided by 150 will be, I think, 6.67 bars, right? Okay, 6.67 multiplied by 113, which is 113 is T12 is 113. Okay, or you can do it like this. Because we are doing a T12 150, so we look at this one. Okay, it means I'm looking at here. This might be. Okay, so here, so instead of, it's the same. So instead of doing a 1000, so I base on the spacing of the river. In this case is 150. 150. Okay, and my area of this bar is 113. 113 meters square. And then d minus x is 104. Okay. Okay. Okay, follow this one, follow on. Okay, this BT here is basically the spacing of the bar. Okay, 150 and this one. Okay, so what's this value here? So this is epsilon 2. What I got is 7.57 times 10 to the negative 4. 10 to the negative 4. Okay. So let me just say is 0.7566. Okay, right. Yeah. That's right. If you look at the units here, this is millimeter, this millimeter, so the millimeter cancel out. Okay? And here is millimeter square. So this one is millimeter square, also cancel out. ES is MPa. This 1.5 actually is a 1.5 MPa. So they didn't show you what they are. This 1.5 is actually the concrete tensile strength that they are assuming. Okay. Understand? So this epsilon 1 is calculated based on the concrete has no strength, right? Concrete has no tensile strength. But when we calculate the crack width, okay, there is the concrete has certain tensile strength, and this is actually causing what we call a stiffening effect. So we need to minus the epsilon 2. So epsilon 2 is based on 1.5 MPa of the concrete tensile strength in the tensile zone. Okay. So in this case, what is this epsilon m? Epsilon m, that means it's the mean strength. So it's 1.006 minus 0.7566. 1.006 minus 0.756. 0.57. So it's 0.309. So this is equal to 0.309 times 10 to the negative 3. Strength. Okay? Strength. Okay, so now our maximum crack width is 3 times A crack is 82 millimeter, and epsilon is 0.309 times 10 to the negative 3, and then I have 1 plus 2. A crack is 82 minus C min. C min is the minimum concrete cover. So in this case it's 40 MPa. So here, this is C min. Okay, the code says for water tank you have to at least a 40 millimeter concrete cover for the protection. So, and then divided by H minus X. H minus X is 154. So what's this value? So here is 1.55 bottom, and top is 3 times 82 millimeter times 0.309, 0.076. Okay, 0.6 divided by 1.55. So where is 0.076? 0.04. Zero point 0.05. Millimeter. So the crack width is 0.05 millimeter, which is actually less than 0.2 millimeter. Okay, so remember when we use the T12 at 150, our rebar stress is 144, which we say is not okay because it is more than 115. But as I said, this approach is actually more conservative. So that's how that's why I'm actually showing to you. That means even though the rebar stress is more than 115, but when you calculate the crack width actually is less than 0.2 millimeters. Okay, so that is why this approach is a more economical approach. That means save you money. Okay, but the thing is, you have to run through all these very laborious calculations. So the consultant actually they don't like to do this part. Okay, they just want to stop here. Okay, all right. So especially the consultant normally is very busy when they don't have that much time. So they just have to stop here. So if the contractor or the developer are not very knowledgeable, they just take it based on your advice. Okay? But if they are knowledgeable, they say, okay, can you go ahead and calculate the crack width for me? You know, and we will save them some money. Okay, all right, understand? So let me, so here, here is showing you a calculation of crack width. Okay, this formula, 3a crack epsilon divided by 1 plus 2 bracket a crack minus c link and h minus x. So it's crucial to get this value first. After you get this value, calculate h minus x, d minus x. Okay, because the h minus x, d minus x are required for the calculation of epsilon. Okay. So here, the epsilon m is epsilon m is epsilon 1 minus epsilon 2, and epsilon 1 is the strain at the socket of the slab, where the crack is. So we have, how do you get the epsilon 1? Based on the epsilon s, that means the rebar strain. Okay? Right, we have the rebar stress here, we calculate the rebar strain, the strain at this level. But the strain at the concrete is bigger, okay? Bigger by a factor of h minus x divided by d minus x. Okay? Right. This h minus x divided by d minus x is roughly, what's the value? 154 divided by 104, almost 1.48. Right? Right. Roughly 1.4. Meaning what? Meaning this one is 48% more than the rebar strain. Okay? Understand? Okay. Alright, so that's how we got epsilon 1, then minus epsilon 2. Remember, this one here, this one epsilon s is normally the epsilon, the ES normally is quoted as 200 gigapascal. But this ES here, we need to put it as MPa rather than GPa, okay? Because this will match the units here, 1.5 MPa, the apparent concrete tensile strength. Yeah. Did I do my calculation correct? Especially this one. Okay. Now, if I do not minus this epsilon 2, if I just use epsilon 1, I think this will exceed the 0.2. Because now I'm using 0.309. Epsilon 1 is a 1.066, right? So 1.066 divided by 0.309, that means it's a almost 3.4 times higher. So if I do a 3.4 times higher, 0.05 times 3.4 times higher, very close, 0.17. Okay? Yeah. All right. So that's showing you how to. So let's repeat. Okay. This is the vertical load that we need to resist the overturning moment from the lateral water pressure. Okay. Now, if you look at most of the walls, okay, they will have 2 layers of rebar, and also they will have horizontal rebars also. So we have not covered that. So now, what's the time? Okay, I think I will cover. Talk about how do I determine how much vertical reinforcement at the outer face. Here is at the inner face, right? And then tomorrow I will talk about the horizontal reinforcement. How do I determine the horizontal reinforcement? Okay. Plus 2 o'clock I have to give another workshop for the students in the bridging class. Yesterday I gave the class from 10 o'clock. Today I have another one.